So number 12, big F is the area under the curve of the function little f as you go from 3 to x. The area of the semicircle is 1/2 times pi radius squared, which is 2 pi, and each of these little triangles is 1/2 of a square unit. All right, part A, find big F of 0, which is the area under the curve if we go from 3 to 0. So as we go from 3 to 0, so the area under little f curve is 1/2, 1.5, 2.5. If you go to 0, we've got half of this half circle, so that'll be just pi. So pi and 2.5, but we are going from 3 and we're moving to the left. So this area will actually be negative, a negative pi plus 2.5. What about f of 4? Well, from 3 to 4, the area under the curve given by little f of t is now positive. We don't change the sign, except now the area is below the x-axis, so it is a negative 1/2. All right, lastly, what about big F prime of 0? Well, the big F prime is the derivative with respect to x of this definite integral, and for this we're going to use the second fundamental theorem of calculus. The answer is equal to little f evaluated at the upper function of x. So we will evaluate that with x, and the x value is 0. So we're going to put a 0 in there. And little f of 0 is 3. Recall that with the second fundamental theorem of calculus, this lower limit has no effect on the answer because we're asking about d dx, or the rate of change. The rate of change of what? Of this area accumulating function. And so if we start at 3 and we stop at x, wherever we stop, the rate at which it's accumulating area at that point had nothing to do with where we started. And that's why it's just f of the upper function. In this case, our input was 0. And so the rate of change of the area accumulation, which is big F prime when x is 0, is little f of 0, which is 3. Let's consider just the general idea of a local minimum. Recall that if there's a minimum, you're going to have a negative slope, and as you move to the right, your slope is becoming less negative, less steep, until it's actually 0. And after that, the slope becomes positive, and then a bigger positive, etc. So to find local minimums of big F, we're going to check to see where f prime goes from negative to positive. And f prime is the derivative with respect to x of f, which is the derivative with respect to x of this, which is little f of x by the second fundamental theorem of calculus. All right, to search for the minimum then of big F, we're going to look for when the derivative of big F goes from negative to positive. We know that the derivative of big F by the second fundamental theorem of calculus is little f. So when does this function go from negative to positive? Well, it's positive here. The output of f is positive everywhere until here it goes from positive to negative. So it never goes from negative to positive, so there are no local minimums. And we should say no minimums on the closed interval from negative 3 to 4. All right, so remember that a function has a point of inflection when its concavity changes at that point. For example, here it's concave down. At this point, the graph becomes concave up. We know that we can determine the concavity with the second derivative. When it's positive, it's up. When it's negative, it's down. So, is the second derivative, the concavity, going from positive to negative or negative to positive? Because if it does, then there will be an inflection point there. Well, that will happen when f prime of x changes sign from positive to negative or negative to positive. So the slope of little f here is positive, still positive, still positive, still positive, and right at this point, the slope f prime, little f prime, is 0. And at this point, now the slope of little f, the graph in black, becomes negative. Negative, 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 negative. So right at x equals 0, little f prime, which is big F double prime, change sign from positive to negative, so there will be an inflection point when x is equal to 0. And that's what our answer would look like. The inflection point when x is 0, because big F double prime of x, which is little f prime of x, changes sign there when x is 0. All right, part D for the equation, let's find the slope when x is 2. The slope of big F. So the slope of big F is the derivative of big F when x is 2. And we know that the derivative of big F is little f of x. And we can see that the output when x is 2 is an f of 2 value of 1. So let's write the equation of that tangent line in point-slope form. We'll need a point. We already know the slope is 1. And we know that the x value of the point is 2. So now we just need to know the y value of the point. And that's big F of 2, which is the area under our curve little f as x goes from 3 to 2. And it's a positive half, but we're moving in the reverse direction, so it's really going to be negative half. That's the y value. So when we subtract a negative 1/2, we have y plus a half. And there we go. You should just stop right there. But if you write it in slope-intercept form, then we'll have x, then we have minus 2, and then we subtract that 1/2 from both sides. So minus 2 minus half, minus 2 1/2, minus 5/2.